one more video for this section, and then I think that's probably enough. And then I have some examples at the bottom here. Here is a geometric distribution. There's its probability mass function. And this turns out to be its moment generating function. And then to find expected value, I put in the moment generating function. I take the derivative of it at t equals 0, simplify it. So again, hopefully you're getting the picture. The definition of the moment generating function is just expected value of e to the xt. So if it's continuous or discrete, I either put this into the sum or the integral, and I find a moment generating function, take derivatives, stick in t equals 0, get moments. Okay, and what I did here was just highlight for you, these are the main density or mass functions we've done in this class. I'm just reminding you of what their probability density or mass function looks like. And then over here are their moment generating functions, because every random variable has a unique moment generating function. So here are the basic ones for these random variables. They will always be this way. So I also put this on that probability distribution chart that I gave you. I think I have it down here. Yeah, here it is. So if you go back to that, I had all the important functions on here, even some that we didn't cover. This is a great sheet, right? It shows you support, it shows you parameters, it shows you density function, cumulative. Here's moment generating function, mean, variance. So for example, we can go to the binomial. There's its, this is not annotated. Here's its mass function. Here's its cumulative function, sum up to x. Here's its moment generating function. Here's its mean. Here's its variance. All of these, Poisson, here's the mass function. Here's its moment generating function. Here's its mean. Here's its variance. So this has it for everyone. All the discrete ones, the continuous ones. Here's an exponential. Here's its density function. Here's its CDF. Here's its moment generating function, mean, variance. So this is a nice chart for that. Let's go back to this lecture. And so sometimes people will give you the moment generating function and ask you to go backwards. And again, there's a very nice property. If two random variables have the same moment generating function, then they have to be the same random variable, because moment generating functions are unique. So this is very nice. If for some reason you have a moment generating function and you have two variables, you know that if their moment generating functions are the same, their distributions are the same. So this is kind of a silly problem, but sometimes maybe you'll just get a recognition type problem. Here's a moment generating function. We can find its mean and variance by taking derivatives, but sometimes you want to know something about the random variable. So it'd be nice to be able to go backwards and say, oh, I know what this random variable is based on its moment generating function. And I can't give you one that you haven't seen at all, so pretty much it's going to have to be on this list above. So we'll remember what that looks like. It has an E in the top. You can kind of see it has an E on the bottom. It has to be this one, right? So notice that P, if P is 0.5 or 0.5, that works out. And then this would be 1 minus 0.5. That would work out. So this random variable here, x must be a geometric random variable with parameter 1/2. So what's the probability that x is less than or equal to 2? That's the sum of a geometric from x equal 1 to 2. This is 1/2 to the x minus 1 times 1/2, which is equal to something. All I'm doing is what's the probability x is less than or equal to 2. Here's the mass function, right, for a geometric with a parameter of 1/2, and then I would get the probability. Okay, here's another one, e to the t squared. Here's the moment generating function. What's the probability x is between -1 and 1? So if we went a little bit too far there. Look at your moment generating functions and try to distinguish. It was e to the t squared. P would have to be 0 here, so it doesn't make sense. I'm not going to get a t squared in this one. I have an e to the t, so it's not this one. I get a t squared here, but I'm going to get a t something else over here. So you can kind of see, yeah, if mu is 0, that wipes that out. I could get my t squared here. So actually, if mu is equal to 0 and sigma is equal to 1, then this just comes out to be, right, e to the, let me see, 0, sigma 1. This should be t squared over 2. Is that what? Oh, yeah, so nicely. So I know then that x is a normal 0, 1. That's its mu, that's its sigma. I'm finding the probability x is between -1 and 1. I would go to my table, or I would integrate, and this is going to be around 68%. There's about 68% area within 1 standard deviation on a normal curve. Go to your table if you want to find and subtract or integrate, but it's going to be very close to 68%. And then I just have a couple problems. I'll do these really fast in Maple. So here's my f of x, and I want to find its moment generating function. So this is just expected value of e to the xt, which is, this is continuous, so I'm going to integrate 2x e to the xt dx between 0 and 1, and that's what's going to be its moment generating function. So let's go down here to, I skipped these. Here is practice problem 1. There's f of x, and there's its moment generating function, and that's that. Okay, this one, here's its moment generating function right here. Define this random variable's mean and variance. I'm going to take first derivative at t equals 0, and we'll get expected value of x. And then if I take the second derivative, I get e to the x squared, and then I can do a nice combination with these two to find the variance. So let's go down here, practice 2. Here was the moment generating function. I took the first derivative, I stuck in 0, so this is the mean. I took the second derivative. That's what this little price sign means in Maple, second derivative. Stuck in t equals 0, find variance, moment 2 minus moment 1 squared. Let's plug in 0, 3/4. Okay, last guy. This is a recognition. I don't know, that's why I have to go back. This is the moment generating function of a binomial. You can go back and check on that list. Maybe I have it up here if I have the binomial quick. Yeah, there's the binomial. 1 minus p times p e to the t to the n. Let me see. So, yes, that would make sense. This is 1/3, right? So this is x is a binomial with p equal to 1/3 and n equal to 4 trials. So what's the probability that x is less than or equal to 2 for a binomial? I just put this into its mass function, sum it up to 2. So here's the binomial, and then sum it from 0 to 2. And so that concludes moment generating functions 11.1.